In this question, we are given two functions. Function f maps x to 1 over x minus 3. And the domain is a set of all real numbers except 3. The other function is g, which maps x to x squared. And the domain is the set of all real numbers. The first part of the question is whether fg or gf exists, and to find it if it exists. And the next question is to find the inverse function of f, to find this, and to state its domain. Okay, so let's start. Now, it always helps in such questions to sketch the graphs of these functions. It helps us to see what are the domain and range quite quick, more easily. So let me write this out. For f, x equals to 1 over x minus 3. Okay, let me sketch this. This would look like this, with asymptote at x equals to 3, the curve that goes to minus infinity at t here and plus infinity at that. Okay, and from this graph, it's quite obvious why the domain does not include x equal to 3, because the function goes to infinity since when x is equal to 3, we have 1 over 0, which is not defined. And we can also see what the range is. The range would be the possible y values, and it covers nearly all possible values except 0. You see, there's no curve crossing the x-axis, so fx can't be 0. Okay, so let me make a note of that since we're here. So for fx, therefore, the range is the set of all possible real numbers except 0. Okay, so x can be any real number except 0. Now let's have a look at gx. Gx is equal to x squared. That's the familiar parabola curve. Okay, so in this case, the domain can be any real value, and the range cannot be less than 0. The range must be more than or equal to 0. So let's write that down. Range would be more than or equal to 0. Now, just a note here. When I say x here and x here, the x here refers to the possible values in the range, meaning the possible y values. So thinking about the x here as like the possible values in a set of numbers, meaning that the x here is not the same as, does not refer to values on the x-axis specifically. Okay, so these two x are not connected. Okay, now in order to decide whether f or whether the composite function fg or gf exists, let's the way to think about it is to think about the mapping from domain and codomain for each function in the composite function. So let me start with, say, the composite, or let's start by checking out fg to see whether this can exist. Okay. Now fg means that the mapping will start with g, so we do the mapping with g first, followed by f. Do a mapping with g. So this mapping with g will start from the domain of g, which is all possible real values. So x can be any real number. Okay, and this maps g to the range, which is x can be any number more than or equal to 0. Right. Now, then the next mapping would be by f. Okay, so we have f here that do the mapping, and the domain of f is the set all the possible values of x except 3. So x can be any real number, but it cannot be 3. That is the domain of f, and this is mapped to a range which is all possible real numbers except 0. So here x cannot be 0. So how do we decide based on this information? How do we decide whether this function can exist? The way to do it is this. If we start from a value here and it's mapped to a value here in the range of g, now the function can exist as long as it is possible for f to map that value to the final answer. Okay, and f can do that as long as that value, that answer from g, is inside the domain of f. Now you can see that might be a problem because these are two different sets. Right? A number that is in this set in the range of g may or may not be also in the domain of f. So let's check this. If a number is here, meaning that if a number is more than or equal to 0, would it definitely also be in this domain of f? Okay, let's look at the domain of f. The domain of f can be any real number except 3. So it can't be 3. G range any number more than or equal to 0. But then this would actually include 3. Okay, so what if g happens to map a number from here to 3, then it's not going to work with f, because f cannot map a number starting, well, f cannot work when x is equal to 3. And we know why, because f is 1 over x minus 3. Okay, so just to make this quite obvious, we know when we will get 3 as the answer when we use G for the mapping. We would get that if we start with a value here of root 3, because Gx is x squared. Okay, so if we start with root 3, when you do the mapping with G, you simply square this and you get 3. Okay, but if you want to use this as a composite function, then we need to map the number 3 using f to the final answer. But f cannot take 3 as the x, because if I put 3 into the f, I'll end up with 1 over 3 minus 3, which is 1 over 0. In other words, this is just not going to work. So this composite function does not exist. Right? Simply does not exist. So let's try the other way around. Try GF and see what happens. Okay. So this time, we'll do the mapping with f first. And the mapping with f starts with the domain where x can be any value except 3. So x cannot be 3. Okay. And it maps onto the range, which is x, any value except x equal to 0. So x cannot be 0, but it can be any other real values. And for G, I'll just copy this out. X can be any real value, and G maps this to x that is more than or equal to 0. Okay. So let's apply the same idea as before. We need to determine if the values in this range, right, if all the possible values in this range are also inside the domain of G. Because if there are some values here that are not inside here, then G is not going to work. So in this case, the domain of G is all possible real values. And that would of course include this. This range of f is all possible real values except 0. But G is all possible real values. So that includes all possible numbers. So therefore, in this case, there's no problem. Right? Any value here can be mapped onward by G. So this time, GF exists. Right? So that's fine. And for this part of the question, we must also explain. We must also find GF. Okay. So let me write this out. GF of x is equal to G fx is 1 over x minus 3, and G is x squared, so I need to square that. 1 over x minus 3 squared, and that's the answer to the first part. Now let's move on to the second part. In the second part, we need to find the inverse function of f. So we need to find inverse of fx, f inverse x. Now let this be equal to y. Now the usual way to do it is to start by saying that fy must therefore be equal to x. Okay, because if the inverse function is from f to y, then the original function will map y back to x. Okay, then the next step, we could make use of the expression for f and write this out in full. So this will be 1 over y minus 3. 1 over y minus 3 equal to x. Now with this equation, we can now solve for y. Because if I can solve for y, then I would basically have the formula for the inverse function. Okay, so let's do that. Let's multiply both sides by y minus 3. That gives x, y minus 3x. And I want to solve for y, make y the subject. So this, add 3x to both sides. This, and then divide both sides by x. So I get y equals to 1 over x plus 3. And here we have the answer. This is equal to y, which is the inverse function. So therefore the inverse function is 1 over x plus 3. Now for this part of the question, we also need to state the domain of the inverse function. Now just by looking at this, the domain is, we can sort of guess that the domain is most likely all possible x except 0. Okay, but we can't just guess the domain like that. We have to go back to the original function and check to make sure that and check what the range is. Okay, because the inverse function, the domain of the inverse function is the range. See, the fx maps from the domain, which is in this case the all possible x values on the x-axis, to the range, which is the possible set of y values. Now we have already seen in the beginning that the range of f is all possible real values of x except all possible real values except 0. And so this would be the domain for the inverse function. Okay, so the domain is x can be any real value except 0. That's the answer to the second part.